To synthesize ATP requires the input of energy. That is, it's an exergonic reaction. And to see what I mean, if you try to synthesize ATP, and this is the energy, the reaction starts out here with ADP and inorganic phosphate, and you need to put in a lot of energy, 7.3 kcal per mole, to synthesize ATP. And in order to do this in our body, the energy of fuel oxidation is coupled to ATP synthesis. And there are two ways that this is done in our body. There's substrate level phosphorylation and oxidative phosphorylation. For now, let's talk about substrate phosphorylation. And as an example, let's use phosphoenolpyruvate being converted to pyruvate. Phosphoenolpyruvate, we learned, has a high energy phosphate bond. And so it's the substrate, phosphoenolpyruvate, which provides the free energy to synthesize ATP. And this is a very exergonic reaction, minus 7.5 kcal per mole. Now to see how this works, let's look at the two reactions separately. We have the synthesis of ATP from ADP plus inorganic phosphate. And this reaction is unfavorable, so I put the arrow mostly to the left to synthesize ATP. And we already saw that standard free energy was plus 7.3 kcal per mole. And then we also have the free energy from hydrolysis of the phosphate group in phosphoenolpyruvate, which I'm abbreviating PEP, which is very favorable. So the arrow goes mostly to the right, hydrolyzed to form pyruvate plus inorganic phosphate. And the free energy for this reaction is minus 14.8 kcal per mole. And when you have two reactions that are coupled like this, you can just add up the reactants and product. So we cancel out the phosphate groups. We have phosphoenolpyruvate going to pyruvate, the product, and we also have ADP as a reactant, and now we have it going to ATP. And if we add up these free energies, we see that it adds up to minus 7.5 kcal per mole. So the energy for making this reaction favorable comes from the substrate, which in our example was phosphoenolpyruvate. Now let's look at oxidative phosphorylation. And the overall reaction for oxidative phosphorylation is shown here. It involves oxygen, which is an electron hog, so the oxygen gets reduced by these electrons and protons to water, and that favorable reaction is coupled to the synthesis of ATP. And the electrons and protons come from these cofactors NADH and FADH, which were generated during fuel oxidation. And the coupling comes not from substrate, but from an electrochemical gradient of protons. So we're going to draw this as a delta mu H plus. There are protons, a gradient of protons across the mitochondrial membrane. So here we have a cartoon of the inner mitochondrial membrane And in this membrane, it's impermeable to protons. In this membrane is the respiratory chain, which we're going to call the electron transfer chain. It's a series of 4 complexes that take the electrons and protons from NADH and FADH, and those are used to reduce oxygen to water and then pump protons across the inner mitochondrial membrane to the intermembrane space. And this creates a gradient of protons. And the enzyme that uses this protons are the ATP synthase. So this ATP synthase uses the gradient of protons created by the electron transfer chain to synthesize ATP. And so that's the two ways that you can couple the free energy of fuel oxidation to ATP synthesis.